All right. So hello, everyone. This is Susie from the Inland Empire team. Also presenting today are Michaela from the Inland Empire team and Melanie from the Sacramento region. So we will be providing an overview of GIS, some basic processing tools, and an example of how to apply GIS to climate change. Okay. So I will start by introducing what GIS is, discussing what a map projection is, and explaining the different types of data. Then Michaela will take over and present several of the basic geoprocessing tools that can be used to manipulate data. And finally, Melanie will finish up by presenting a GIS project her team has been working on as part of CivicSpark. So let's get started. So most of you have probably had some exposure to GIS, but I will briefly introduce what GIS is and what some of its benefits are. So GIS is a technological field that incorporates geographical features with tabular data in order to map, analyze, and assess real-world problems. So in other words, GIS takes data that is referenced to locations on the Earth and manipulates its accompanying attribute table, its attribute data, to create a map that can be analyzed. So, reading through pages and pages of data won't mean much to a reader without reference to the location of that data and its relative location to other data points. So GIS enables the data to be presented and interpreted in a visual form so that it can be analyzed to understand relationships, patterns, and trends. So who uses GIS? Well, GIS benefits organizations of all sizes and in almost every industry. International organizations like the World Bank, the United Nations Environment Program, and the World Health Organization rely on GIS to share data visually. Small and large private industries use GIS. There are also many applications for GIS in government. So I'm sure most of you guys that are working in local governments have seen that, the staff usually has a full-time GIS member who works on things like land use maps and engineering projects. So GIS is also used by nonprofit organizations to share data with their supporters and to shed light on important issues by creating powerful maps. Also, academic and research institutions use GIS mapping to analyze and interpret their data. So what kind of things can you do with GIS? Well, this is a pretty short list of possible uses, but the list could go on indefinitely. You can really map anything. Some common uses are environmental impact assessments, resource management, land use patterns and land use planning, change detection, so things like changes in annual temperature and changes in greenhouse gas emissions over time. There's also a lot of GIS uses in transportation planning and a lot more. For an example of kind of a miscellaneous map that can be made, is this map on the bottom visualizing California sheep flock and wool quality. So to some business out there, this map is useful, maybe to help them select the finest wool out there. So perhaps this is even used by Smart Wool to make their socks or something. But there are a lot of uses for GIS and many different reasons you would need to make a map. So here's a map from NOAA showing the U.S. drought conditions. NOAA is constantly updating these maps. This one is from the end of March. This is a pretty simple map, and your eyes are probably just drawn to the dark red because we need a reminder of how bad the drought is here in California. But imagine if instead this map there was just thousands and thousands of data points on an Excel spreadsheet. Would you be able to see where the drought was occurring? Would you realize that Texas and Oklahoma are also experiencing exceptional drought? Most importantly, your average citizen isn't going to look through thousands and thousands of data points, but this map allows anyone to examine the data visually and draw their own conclusions. Hopefully that conclusion is that we need now, but it enables everyone to visualize the data. So now I will talk more about the actual GIS application. Every data set has a coordinate system, which is used to integrate it with other geographic data layers so that they are in a common coordinate framework. If your data sets have a different coordinate system, they will not overlap and your data will not be displayed correctly. So on the right are examples of a few of the different map projections. So you can see that each is different and how the different projections wouldn't quite overlap on one another. If you had two different data sets, each with one of these different ones, they wouldn't overlap and the data would be skewed. So remember that all the data sets that you bring into GIS for your map should have the same projection system. So there are two main types of data, vector and raster, and vector data is displayed as points, lines, and polygons. So that would be things like streets and customers, trees and schools, things like that. Raster data is cell-based data, such as aerial imagery and digital elevation models. So this could be things like elevation and greenhouse gas emissions. And behind each of these spatial features is attribute data, which is the additional information about the spatial features. So, for example, the location of the school would be spatial data, but the information behind that data point, such as maybe the school name, the level of education taught, maybe races of student population, student capacity, that would be considered the attribute data, like the data behind the point. And so here is an example of an attribute table. This table displays all the information behind each spatial data point. And this attribute data can be manipulated and mapped using different geoprocessing tools. So this is where I'm going to pass the presentation off to Michaela, and she'll talk about some of the geoprocessing tools available to manipulate data.
Okay. Let's see. Okay, I just wanted to make sure that I could move through slides. Okay, so my name is Michaela. I'm also in the Inland Empire region, but I'm working out of a different office from Susie. So today I'll be going over some specifics in ArcGIS. They'll hopefully give you a little bit of a background on the type of abilities the software has. So geoprocessing is a major function in ArcGIS, and it's crucial for performing any kind of spatial analysis, which is a major strength of ArcGIS. So basically today I'll talk about some basic geoprocessing tools. So we'll go over overlays and spatial joins, and then some specific tools that can help you with your analysis. So basically, these geoprocessing tools allow for the analysis of relationships between spatial data. So it can answer spatial questions in both a visual manner through the maps and the outputs it creates, and also a numerical or categorical manner with the attribute table. So specifically, one thing that's important to note about geoprocessing, and Susie touched on this, but it's very important to make sure that all the data layers are in the same projection coordinate system before you begin any geoprocessing tool. This is just important because if the geoprocessing tool even worked, your map would be really skewed, or it just would kind of freeze your ArcMap, and you don't want that to happen. So all of these geoprocessing tools can be found in ARC Toolbox, which is on the top bar in your ARC map. So first I'll just talk about the difference between an overlay and a spatial join. So both overlays and spatial joins are methods for combining information between GIS layers. The major difference between the two is that a spatial join doesn't alter the original geography in any way. It simply joins the attribute tables of two layers together based on their common spatial locations. So you can kind of see the difference here in these side-by-side maps. So overlay types. Overlay feature classes are a combination of multiple feature classes. The best way to understand this, I think, is by seeing this visual representation here, where we have a geology feature class and a land ownership feature class. And then that last layer is a result of an overlay between the two. So, and also, we'll use the term feature class and layer kind of interchangeably in this kind of discussion. So the main type of overlay is overlay with attributes. I also have on here extraction, but I won't go into that today. It's also important to note here that ArcGIS doesn't recalculate anything like area, length, or perimeter in your new shapefile. So if you are needing those kinds of analysis, then you should be using the calculate geometry tool in the attribute table. Okay, so overlaying with attributes combines attribute tables based on common data. So you can kind of see here both the maps themselves, and then these little screenshots are from the attribute table, and you can see that those fields and values are being combined. Okay, so the easiest way, I think, of accessing geoprocessing tools is through ARC Toolbox, which I mentioned before you can find on that main bar on ArcMap. So depending on which type of ArcGIS you're using, the availability of tools will vary. I know that there's an online version of ArcGIS, and I haven't used that one extensively, but I do think some of these tools we talk about today, there's a possibility that they wouldn't be available on that. If you have like a student license of ArcGIS or the full-on version of it through your municipality, then these tools will definitely be available. And then one last thing is that the result of these geoprocessing tools is almost always going to be a new layer on the map, which is really nice because it gives you the kind of flexibility to do some sort of analysis and then go back and remove it, and you still have your original feature classes. Okay, so the first geoprocessing tool I'm going to talk about is Dissolve. So this tool combines feature classes in a single layer based on a similar attribute value. An example displayed here would be if you had one layer for streets, and then this on Main Street, there are small segments of it on different blocks. And in your attribute table, it's going to be displaying that as all different streets. And you'd want to use the Dissolve tool to combine all those into one street to represent how it actually is in real life. This function begins to be really important when you're actually creating new spatial data. So as you get further into ArcGIS, it becomes a really common tool you'll be using. Oh, okay. Let's see. Oh, okay. Sorry about that. So this is just a kind of gives you a screenshot of what the Dissolve function looks like when you're using ARC Toolbox. Okay. Sorry, it's kind of slow. Okay. So the next tool I'll be talking about is Clip. The Clip tool will reduce the extent of one layer based on the extent of another layer. So an example of when you would be using the Clip tool is if you had one layer that's streets and that extends through all of Los Angeles, and another layer that's just an outline of downtown Los Angeles. So if you wanted to only display streets within downtown, you could use the clip tool to create a new feature class of just downtown LA streets. And in this example, the input layer would be streets, and the clip layer would be the outline of downtown. So the street, and in this example, the streets layer's attributes are not actually altered. Another geoprocessing tool is called Intersect. It's being slow, sorry. Okay. The Intersect tool compares common ground between two data layers, and only the common areas will remain. So for example, if you wanted to compare something like a loamy soil type and organic farmland, you could intersect a data set with land and soil, and then land dedicated to organic farming. So the result would be a new feature class that displays only land that both has loamy soil and is also used for organic agriculture. And then sort of similar to this is the union tool, but when you use the union tool, the extent of both feature classes still remain. So in kind of using that last example, a union would display all land with loamy soil and all organic farming land. With land that has loamy soil and is also dedicated to organic farming would be highlighted. So, and union versus intersect, this kind of just displays what the difference between those tools that I just talked about. So this slide I think is really helpful in simplifying the usage of these geoprocessing tools. So the clip and erase tools do not join attributes, while the intersect and union do join attributes. So something that's really important to know is knowing which file will be your input file and which will be your overlay, and that just depends on what type of analysis you're looking to do. So we have the merge and append tools. So the fields on that must match exactly. On to buffering. The buffering tool does pretty much exactly what it sounds like it would do. It creates a given radius around an input layer. The buffering tool has a lot of different options, a lot of different ways of specializing it, and you can use a specific distance for a buffer. You can create a variable width, single ring, multi-ring, and you can also dissolve part of the buffer. So it basically depends on what kind of analysis you're looking to perform with that. So this is an example of a buffer with and without dissolved barriers. So you can basically decide whether or not you would want this based on the attributes of your feature class and what kind of analysis you're looking to do. So this is a good example of how buffers can be more informative after subsequent tools used for analysis. So the map on the right could represent city streets, and this is just my conjecture. I didn't make this map. So, but for example, it could be representing city streets, and the buffer around it could represent anything from, how much the region surrounding it that's affected by, noise or emissions or that kind of thing. So in that sense, it can be pretty informative. And then this is just a screenshot of the menu for the buffer tool, and it's highlighted just so that you can see the areas that you can specialize within it. And then geoprocessing tools, this is also just a screenshot of a geoprocessing tool menu, just so you can have some sort of familiarity with the way that you're entering information in these sort of dialog boxes. And one last important note is that, especially in geoprocessing, but as with almost everything you do in GIS, it's really important to be patient because these dialog boxes can sometimes move very slowly. And when you, like I sometimes did, if you get a little impatient and try to click things, it can crash your whole ArcMap. So you don't want that to happen. So yeah, it's just important to have that patience with this. And with that, I think we'll hand it off to Melanie, and she'll go over the kinds of ways she's using ArcGIS in CivicSpark.
Hi everybody, my name is Melanie, and I think I have control of this presentation. Okay, yes. So my name is Melanie, and I'm from the Sacramento region, and I'll be giving a presentation on how I use GIS in my CivicSpark project. So the organization that my partner Laura Moser and I are working for is the Sacramento Council of Governments, or abbreviated as SACOG, and they are the regional metropolitan plan organization who oversees transportation planning within the 6 counties of Sacramento, Yolo, Sutter, Yuba, Placer, and El Dorado. SACOG is responsible for developing the federally required Metropolitan Transportation Plan and the newly state-mandated Sustainable Community Strategies Plan that assesses population trends, economic vitality, and travel patterns through a 30-year horizon in order to adequately meet air quality goals and finance appropriate transportation projects and programs in the Sacramento region. This plan gets an update every 4 years, and in the next update that's coming up in 2016, Laura and I have been working on a climate vulnerability assessment component that evaluates some of the climate risks in our region. So our main evaluation in the report looks into heat, wildfire, precipitation, and runoff. And so onto data collection. Susie had talked about this a little bit earlier in her segment, but I just wanted to review this over again. So there are 2 different ways of representing the real world into 2D formats within GIS. Vector data are represented as points, lines, and polygons, and they're usually used to store discrete data with discrete boundaries, such as streets and roads, administrative boundaries, kind of like city limits, county limits, and other types of local boundaries, land parcels, and buildings. Raster data, on the other hand, breaks up the real world into grids of cells and are used to store more continuous data that have no distinct boundaries, such as land cover, vegetation, elevation, and pollution concentrations. For the purposes of our research, climate data would then be considered as raster data because they don't have any distinct boundaries in terms of where they concentrate. And so, fortunately, for our research, the California Energy Commission began developing an online CalAdapt tool to synthesize some of the California climate research and scenarios that can be beneficial for local decision making. And some of the data sources from this website comes from scientific research organizations like the Scripps Institute, the Pacific Institute, U.S. Geological Survey, UC Berkeley, UC Merced, and Santa Clara University. Here in this tab, what's showing up? here in this tab, you can see that we can access some of the raw data in Excel or GIS-friendly formats. In this PowerPoint, we'll be looking into maximum temperature and evaluating temperature rise in the Sacramento region. In the CalAdapt tool, you can acquire data that dates from January 1950 until December 2009 or 2099, which gives you some of the historical data that they've collected and some of the data projected into the horizon year by the end of the century. The data also is also projected under two different greenhouse gas emission scenarios, A2 and B1, A2 being the higher emission scenario and B1 being the lower, as well as some of the four global climate models that are used widely around the climate scientific community that uses different mathematical models that give varying weights to atmospheric and physical inputs to project some of the future climate scenarios in our in the climate change science. So when you finally select the date range that you want your data for, it will come into a zip folder with tons and thousands of geotip images. These images give you monthly snapshots of our data from 1950 until 2099. When uploaded into a GIS program, it will look a little bit like this, kind of like a grayscale image of California. Also, within the zip file, there's also a thing called metadata, and metadata literally means data that describes other data. Most GIS data that you'll find will have this simple text document named metadata that gives you some basic information about the purpose of the data, the sources, the units of expression, and some of the additional notes that the distributor wanted to make about the data itself. And so onto data processing. In our methodology for the vulnerability assessment, my awesome partner Laura actually built some basic Python scripts to make some charts and graphs off of the raw tabular data from CalAdapt. In the analysis, we identified July as our hottest month under both high and low emission scenarios. And then we divided our horizon year into 4 different 30-year time periods, with 1980 to 2010 being sort of our historical baseline year. Then we used a tool called map algebra to calculate the raster average along each grid cell within the designated 30-year time period. And so this is sort of what the, when you open up ArcGIS, this is what the blank canvas looks like. And I first started with building out 4 different data frames for each of the 30-year time period. And starting with the historical period, I used this Add Data button to load the geotip images into the data frame. And I selected, this is kind of slow, I selected all of the July months into the data frame and loaded it onto there. As you can see, once the data is loaded, the topmost layer in the table of contents is usually the one that will be displayed on the screen. And here it will show you the maximum and the minimum values within that image content. And in the metadata, it actually tells you that the data is stored in Celsius. And so to take advantage, or to move on to the average of this data frame, we wanted to look into the map algebra or the raster calculator within the ARC toolbox. And the ARC toolbox has a plethora of awesome geoprocessing and geoanalytical functions that you should probably take, a couple of GIS classes to fully really understand the amazing things that GIS can really do for you in map making. But anyways, so in order to take the average of the raster, or take the average of the data layer, we have to search for the raster calculator under the spatial analyst toolbox, and under the map algebra folder, you'll see the raster calculator tool. Once you click on that, you will see the calculator pop up, and here you will have to input sort of an equation to just a basic algebra equation to sort of add up all those layers and then and divide it by how many layers you had. And here it's really important to make sure that your syntax is right so that your calculations won't come up with some weird numbers, or that you'll come up with an error message when you do the calculations. Sometimes if you make a mistake in your calculation and you don't notice it, it can be quite messy to deal with it later on in your analysis. So here it is, here in the top, this is the raster average for the historical baseline year of 1980 to 2010. And I wanted to convert this again with the raster calculator from the Celsius into Fahrenheit. And so here I inputted the conversion equation, and taking that layer, I have a new layer with our raster average in Fahrenheit. And so this is our raster average for the Fahrenheit layer, and then my next step is to extract the data within the SACOG boundaries that binds the 6 counties in our region. And I click on our data view button on the bottom. So here's Fahrenheit, and here's a data view. And the data view option lets you look into a data frame specifically. And here I loaded a SACOG boundary layer, and note that this is a vector layer, so that has different properties than the raster layer underneath it. As Michaela mentioned earlier, I needed to clip the layer so that the input layer can be clipped around the boundaries of the vector layer on the top. And so I go into the data management toolbox, and I find the raster processing folder, and I click onto the clip tool. Here the clip tool calculator will pop up, and I load into the appropriate input raster layer, which is the Fahrenheit layer, and then I also add the county layer, which is the extent clip boundaries that I want my data with. And I also click this checkbox to make sure that the features are being clipped right around the boundaries of the SACOG counties. And this is what this looks like. So in default, it kind of displays the boundaries into this black and white stretch mode, which gives you a ramp, which displays your data into a ramp of colors that usually that's usually best used when you have a large range of values to display with continuous raster data. It's like imagery and aerial photographs. And so when I click into the properties of my data layer, I will get this data layer properties page, and I look into this here to sort of display the data into various modes. And so in order to sort of show and break up my data into different temperature ranges, I want to display my data into the classified mode. And so here it is, the classified mode, and the classified mode lets you kind of group the cell values by classes and assign specific color themes for each group. And here right now it's in black and white, but you can always change the colors here in this color ramp right here. And so when you click on that classified button, it'll give you, well, and yeah, here I changed the colors for the color ramps. And then when I click on the classify button, it'll give you more advanced functions to manually adjust the class breaks and some of the basic overviews of the geostatistics and the distribution of the data within your data set. And our purposes to capture the wide range of temperatures in my data, I gave it 7 classes and manually adjusted the break values into 5-degree groups. And so here you can see this transition. Once I finish that, this is sort of what the data looks like, and now it displays all of the different regions that fall under a specific temperature category. And I repeat the step basically for each of the time period from 2011 to the end of the century of 2099. And on to the final results. So I here this map here evaluates some of the temperature increases under both emission scenarios in the month of July from 1980 to 2099. And as you can see here, temperature is going to gradually increase under both emission scenarios. As you can see, sort of the slow appearance of the red grids kind of popping up at the end of the century. But the A2 scenario, the higher emission scenario, will be seeing a more drastic increase by the end of the century. And then similarly, I repeated this process with the other climate conditions, and here it is for fire potential. And we can also see it similarly that fire potential will be increasing for both high and low emission scenarios, with the highest risk being within the Placer and El Dorado counties, but there will be more drastic increases under the higher emission scenario. For precipitation, precipitation was a little tougher to evaluate because of the fluctuation in just precipitation processes and some of the different factors that, or different weights that different models give into precipitation projection. And so here you can see under the high emission scenario, we'll see a progressive increase of rain by the end of the century. However, though, in the low emission scenario, that's not seen in this PowerPoint. It actually projects the opposite trend of seeing a decreasing precipitation trend by the end of the century. So yes, that's basically the climate vulnerability assessment that Laura and I have been working on for the past few months. We basically spent a lot of time the past few months just playing around with CalAdapt data and sort of dabbling into this with really not a lot of experience into what climate data is really about. But thankfully, CalAdapt has made it really easy for us to do this research. And I've only really taken an introductory course on GIS, but I definitely recommend everyone to just look into local community colleges that may offer GIS courses, because GIS is definitely a hands-on program that requires a lot of trial and error and just sort of just a lot of things that you should just try out for yourself. So yeah, take in local community college courses or any online courses that might be offered on like Coursera or edX, and some of the resources that Andrew has outlined for you in the Google Doc. And yeah, and there will be lots of trial and error as you go through this, so make Google your best friend. And if you have any more questions about GIS and the climate vulnerability assessment itself, feel free to contact me in this email address. And thank you very much for participating in this webinar.
Thank you, Melanie, and thank you so much, Michaela and Susie as well. That was a fantastic overview of GIS and specifically how you can use it for CivicSpark. We do have just a few minutes, so right now I don't have any questions that have come in today. But if anyone does have any questions that they want to ask either Melanie, Michaela, or Susie, please feel free to go ahead and type them. And I will say, just following up, Melanie just mentioned this, but we will be getting out a list of resources as well for those of you who are interested in sort of following up and doing some homework on your own as to learning GIS and sort of figuring out how you might use it for your project. So I'm expecting to get that out hopefully later this week. Drew up in the North Coast asked, which model did you use and primarily why? Did the models only differ greatly for precipitation or in any of the other attributes that you were looking at as well?
Yes. Hold on, let me go back to the precipitation slide. So we've kind of played around with this many times, and as you can see here in the top, we sort of, in this map, we actually took a model average of all 4 models that were given by CalAdapt. But in other reports that we've read and other transportation agencies that have done this analysis, there's varying methods of which models to use because every model kind of has a more takes precipitation inputs more sensitively than others. And so GFDL actually, this first model here actually tends to be sort of the drier model, and then this PCM1 tends to be sort of the wetter model. But I think that also varies depending on the geography of your region. And so for that purpose, we just sort of said, let's just take an average of everything and sort of kind of hit the midline of all of those models and just see what we get. And we have other maps too of the different, the wetter and the drier models that I haven't displayed. But if you want to check our report, we're definitely welcome to. We are definitely open to sending it out to other CivicSpark members to check it out, and we would love to hear some comments about our methods as well.
Excellent. Well, it doesn't look like we have any other questions that are coming in now. If anyone does have any questions, please feel free